Dear students, welcome to my next session on solid state. In the previous class, I was explaining the classification of the crystalline solids into molecular crystalline solids and ionic crystalline solids. I told you that all the crystalline solids will be classified into four types based on the intermolecular forces. The first type of molecular crystalline solids is molecular crystalline solids. Second type is ionic crystalline solids, and the third type is metallic crystalline solids, and the fourth type is covalent or network crystalline solids, in which already I had explained the general characteristics of molecular crystalline solids. I told you that molecular crystalline solids will have constituent particles, molecules. Molecules are the constituent particles in the molecular crystalline solids, and the intermolecular forces are van der Waals forces, that is dispersion forces or dipole-dipole forces or hydrogen bonding. I also told you that molecular crystalline solids will be classified into polar, non-polar and hydrogen bonded. And the second type of crystalline solids are ionic crystalline solids, and the constituent particles in ionic crystalline solids are the ions, that is positive ions and negative ions, cations and anions. And the intermolecular force is electrostatic forces of attraction between the opposite ions, that is anions and cations. And now we move to the next classification, that is metallic crystalline solids. So what are the constituent particles in metallic crystalline solids? In molecular crystalline solids, molecules are the constituent particles. In ionic crystalline solids, ions are the constituent particles. In metallic crystalline solids, metal ions are the constituent particles that are surrounded by the electrons and held by the attraction forces. Once again I will tell you what are the constituent particles here. Metal ions are the constituent particles. Metal ions means metals form cations. So metal ions will be constituent particles that are surrounded by electrons. So these metal ions are surrounded by electrons. So metal ions are there and that are surrounded by the electrons. Electrons are negatively charged, metal ions are positively charged. Now the force of attraction between the metal ion and electrons will be the metallic bond. What is a metallic bond? That is the attraction between the metal cation and electron. So what is the bonding presenting in it? Metallic bonding. What is the force presenting in metallic crystalline solids? That is nothing but metallic bonding. In molecular crystals, van der Waals forces. In ionic crystals, Coulombic forces, that is electrostatic forces of attractions. In metallic crystalline solids, the bonding is metallic bonding, or the binding forces are metallic bonding. But how these metal ions are formed and those are surrounded by the electrons? Actually, we have electron motion theory or electron C model that explains the metallic bonding. Metallic bonding is entirely different from ionic bonding and conventional covalent bond. It is metallic bond. It is according to the electron motion theory. All the metals to form metallic bond, or if you take any metallic crystal, all the metals will lose one or more electrons to form metal cation known as kernel. So here you can look here, if this is the metals are electropositive. Electropositive means that have the tendency to lose electrons. How many electrons will they lose? They lose electrons based on their valency. If 1 is the valency, they will form unipositive cation. If 2 is the valency of the metal, that will lose 2 electrons to form dipositive cation, and so on. So metal being electropositive, that will lose electrons to form metal cation. So here this metal cation is known as kernel, K-E-R-N-E-L, kernels. So all the metals, if all the metal atoms presenting in the metallic crystal will lose one or more electrons based on their valency to form kernels. So kernels means that is nothing but metal cation. You can look here, for example, for all the metals are losing electrons, being electropositive, they will form metal kernels. These are metal kernels. What I am explaining is electron ocean theory. Electron ocean theory explains the bonding in metals. Metallic crystals can be explained better by taking electron ocean theory. According to electron ocean theory, in a metallic crystal, the metal atoms will lose electrons to form kernels. Kernels means nothing but metal cation. If it is zinc means it will form zinc plus 2. Likewise, if M is the metal, it loses one electron, it will form M plus. Now the electrons last will be forming a pool of electron or ocean of electrons. Here this is ocean of electron. Pool means a pond here. So this is the ocean of the electrons. So if you take a sample of crystal here, the crystal consists of kernels, metal cations, and the electrons lost by the kernel will be forming a pool or ocean of electrons. These red circles are nothing but electrons, ocean of electrons. In this ocean of electrons, these metal cations are immersed, kernels are immersed. Kernels are there in the electronic ocean. This is electron ocean, a pond of electrons. In this electrons ocean, kernels, metal cations are floating. Now the attraction between the metal cation and electron is known as metallic bonding. Metallic bond is nothing but the attraction force between the kernel, that is metal cation, and the electron. So what is the bonding present in? Metallic bonding. So this is metallic bonding. So metals will have metallic bond, and that has been explained by the electron ocean theory. According to electron ocean theory, all the metals will lose one or more electrons based on their valency to form kernels, nothing but cations. These kernels will be floating on the electron ocean or electron sea. And now there exists an attraction between the electrons and the metal kernels. This is nothing but metallic bonding. It is the attraction force between the metal kernel and the electrons. Now let us go for the characteristics. You all know that metallic crystal means you can take gold, or you can take silver, you can take copper, zinc, iron, etc. These are all metallic crystals. In all these crystals, such type of metallic bonding will be existing. Now let me explain the general characteristics of these metallic crystals. So metallic crystals consist of metal ions that are surrounded by the electrons and held by the metallic bonding. Metallic bonding means attraction force between the metal cation and the electrons. And now let us go for the general characteristics. Generally, we all know that metals are very hard. So here what is the first characteristics of the metal? They are very hard, but they are malleable and ductile. Malleable and ductile. You know that ionic crystals are so very hard, but when you hammer that ionic crystals, that will be brittle, that will be broken into pieces very easily. But here the metallic crystals are very hard, but when you hit with the hammer, that will be stretched into a sheet. Malleability means stretchability into sheets, thin sheets, and ductiles, stretching into wires. A metal can be stretched into wires. You can see copper wire, aluminum wire, how they are made by taking the metal and stretching them into a wire due to its ductility. Ductility means stretchability into wires. Malleability means stretchability into sheets. Now these have high to moderate to high melting points, fairly high melting points. Metallic bonding is strong, and so these are very hard, and so these will have moderate to very high melting points. And these are very good conductors of electricity. Good conductors of electricity. We all know that metallic wires, good conductors of electricity. Why these are good conductors of electricity? You know that according to electron ocean theory, we have free electrons here. A metal is the metal cations, that is kernels are floating in the ocean of electrons. So we have free electrons here. So as we have free electrons, these are good conductors of electricity. What is the reason for it? Due to the availability of free electrons. And it is a good conductor even in the solid state or in its molten state. If you take any metal either in the molten state or in the solid state, they are good conductors. Ionic crystals are not good conductors in the solid state. Why? In ionic crystals, the ions are held very strongly and there is no any free movement of ions. But here in crystals, we have free electrons. Even in the solid state, we have free electrons. Because of that, they are good conductors of electricity. And also in the molten state, they are good conductors of electricity. We can also say these are good thermal conductors. Thermal conductors means they can transmit heat from one point to another point. So these electrons and the kernels, they can transmit heat from one point to the another point. That's why these are not only electrical conductors but also good thermal conductors. And here I told you that they have very high melting point, that is due to the strong attraction force between the metal kernel and the electrons. So these are the general characteristics of metallic crystalline solids. Now let us move for the next type of crystalline solids. First one is molecular crystalline solid, second one is ionic crystalline solids, third one is metallic crystalline solids, and next one is what we are going to study is covalent or network crystalline solid. The fourth type of crystalline solid is network or covalent crystalline solid. This is covalent crystalline or network crystalline solids. So if you see the title, you come to know that covalent bond will be the binding force here. In molecular crystals, van der Waals forces. In ionic crystals, Coulombic forces, attractions. In metallic crystals, metallic bonding will be the binding force. Binding force means that keeps the particles together. Now here covalent bonding will be there. What are the constant particles here? Mostly atoms will be the constant particles of covalent crystalline solids. Here the atoms are held by strong covalent bonds and these covalent bonds are repeated three-dimensionally. So here the atoms will be bonded covalently. That means one atom will be bonded with the other atom by covalent bond. But these covalent bonds will be extended in all the directions, along the x direction or along the y direction or along the z direction. There will be covalent bonds, very strong covalent bonds. If you understand what is the binding force here, covalent bonding or covalent bond will be the binding force. We can take a diamond as an example for covalent crystalline solid or network crystalline solid. Even you can take graphite, you can take carborundum, that is a silicon carbide. These are all some examples for covalent crystalline solids. Majorly these consist of atoms that are covalently bonded and these covalent bonds are extended three-dimensionally. Let us study one or two examples to know the nature of the covalent crystalline solids. We are going to study the structure of diamond and graphite. Actually we had already studied in our 11th standard, but still we have in our syllabus in the second year, that is the 12th standard. First I will take diamond here. In graphite and diamond, both are having carbon. Graphite consists of carbon atoms, diamond consists of carbon atoms. Both are allotropes. You all know that what is meant by allotrope. So graphite and diamond are allotropes of carbon. We are going to study diamond. In diamond you all know that carbon is sp3 hybridized. Here each dot represents a carbon atom, that is sp3 hybridized. And again you know that this is three-dimensionally repeated here. This is sp3 hybridized carbon and it will form four bonds with other adjacent four carbon atoms. Each carbon will be bonded to the four other carbons. Now look here. This is one carbon atom bonded with other four carbon. This is one carbon that is bonded with other four carbon atoms, and it is tetrahedral. And these covalent bonds are repeated three-dimensional. For example, it again goes, and again here we have covalent bonds again, and this can be extended here. For example, here this can be extended again here, and here also we can have covalent bonds. Look here, it is continuously extending here. So again you can extend this, and again here also you have covalent bonds. Okay, the tetrahedral structure is repeated here, and throughout the crystal such type of arrangement will be there. Again here also you can extend, and here also you can have covalent bonding, here also you can have covalent bond, and so on. It goes on, it goes continuously. So here already you have studied in first view. So sp3 hybridized carbon will be bonded with other four carbon atoms through covalent bonding, and you all know that here the bond length is 154 picometers. So, and you all also you know that diamond is very hard, and it is an insulator of electricity. Why it is an insulator? There is no any free electrons. That is why diamond is very hard. So diamond is an example for covalent crystalline solid, and this is the hybridization and structure of diamond. Let us go for graphite here. In graphite also, I will take graphite now. In graphite also, carbon atoms are held by the covalent bonds here. But here we have hexagonal layers. Look here, this is a hexagon, and here this is one more hexagon. Look here, each dot represents again here a carbon atom. And the hybridization undergone by each carbon is sp2 here. That is the major difference between graphite and diamond. Look here, this is sp2 hybridized. sp2 hybridized. Here each carbon is bonded to three other carbon atoms. Only with three other carbon atoms it will form covalent bonds. Here one carbon is bonded to four other carbon atoms. It uses this all four valence electrons for four covalent bonds. But here it will form only three bonds. Carbon has four valence electrons. After sp2 hybridization, it uses only three electrons for three covalent bonds. The fourth electron will be free here, so it won't use its fourth electron because it is forming here. This is the free electron. Here it is the free electron. Here it is the free electron. At each carbon there will be a free electron. Free electron in the sense here that doesn't involve in the bonding here. This is one layer. You all know that graphite exists in layers. This is one layer, hexagonal rings, and the same type of layer will be existing here. This is one more layer here. This is one more layer of graphite here. So it goes on. So it continues. This is the another layer here. So the distance between these two layers will be around some 340 picometers. This is one layer and this is the other layer. As it has a layer structure, the one layer will be sliding on the other. When you apply stress, one layer will be sliding on the other. That is why it is acting as a good lubricant. Graphite is one of the good lubricants. And here you can see the carbon-carbon bond length here. That is nearly 141.5 picometers. So here in diamond it is sp3 hybridization, and it is sp2 hybridization in case of graphite. In diamond there is no free electron, but in graphite you can see free electrons are present at each carbon. This free electron is responsible for its electric conductance. Graphite is a good conductor due to the free electrons. So here we have free electrons, here no free electrons. This is the difference here. This graphite is very soft and good conductor. Please remember that all the covalent crystalline solids are insulators, very hard and insulators, except graphite. Graphite will be soft and also it is a good conductor of electricity. Let us write the general characteristics of covalent crystalline solids. So what are covalent crystalline solids? Atoms are the constituent particles in covalent crystalline solids, and these atoms are held by covalent bonding in all the three dimensions. And let us write the characteristics of the covalent crystalline solids. The very first characteristics is these are very hard because there is a three-dimensional covalent bond, and these are insulators, all are insulators. But what is the exception? Here exception is given for graphite because that has free electron and it's a conductor, good conductor of electricity. Except graphite. Here also exception in hardness for graphite. And these will have very high melting points as they are very hard and a strong covalent bond is there. Very high melting points they will have. They will have very high melting point due to the strong covalent bond, three-dimensional covalent bonding. And these are some of the general characteristics related to the covalent crystalline solids. But the important thing is both molecular crystals, or it may be ionic crystals, or it may be covalent crystals, or you can take metallic crystals. Every crystal has its own applications. So let us recall all the points. We have four types of crystalline solids: molecular, ionic, metallic, and covalent crystalline solids. In molecular crystalline solids, molecules are the constituent particles. In ionic crystals, ions are the constituent particles. In metallic crystals, metal ions are the constituent particles. In covalent crystalline solids, generally atoms are the constituent particles. And majorly, what I want to say is the forces of attraction, intermolecular forces are in molecular crystalline solids, van der Waals forces will be the intermolecular forces. In ionic crystals, Coulombic force of attractions will be the intermolecular forces. In metallic crystalline solids, metallic bonding will be the metallic bonding will be the intermolecular force, and here in the covalent crystalline solids, the covalent bonding will be the force, intermolecular force operating. This is the classification and some of the examples related to the crystalline solids. In the next concept, we will study the next concept. Thank you.